Thank you so much for coming to this video. So today we're going to be going over how to model motion under gravity and also projectiles. So please review the videos on constant acceleration formulae, trigonometry and vectors, as we're going to be using that in this video. So the learning objectives are to be able to model motion under gravity in a vertical plane using vectors, and also to be able to model the motion of a projectile as a particle when moving with constant acceleration. So I'm going to be teaching you how to derive some of the key equations that we need to know for projectiles, and also how to apply this to some practice questions. So like always, there's going to be timestamps in the description of the video, so feel free to skip to any parts you want to, but let's get started. So a projectile is just anything that, if you have a particle like a ball or something and you're just throwing it into your air, that's just called your projectile. So if you have a particle that's projected with the speed of u, so u being your initial velocity, at angle of alpha to your horizontal, then you can split your velocity into two components. So this is with a right angle triangle. Your horizontal component, that would just be your u cos alpha, and your vertical component, that would be u sine alpha. So once you've split your velocity into two components, then you can just solve your projectile questions just normally using our CVAT equations. So let me just go through how we split it into u cos alpha and u sine alpha quickly. So this is just using trigonometry. So if you were first to work out your x component, your horizontal, you can just say that cos alpha, that's just equal to your adjacent over your hypotenuse, so just be x, and your hypotenuse of your triangle is just u. So that means your x is just u cos alpha, and then for your y value here, you can say that sine alpha, which is equal to the opposite of over your hypotenuse, that's just equal to y over u. So that means y is just u sine alpha. So that's why if you have a velocity that's projected with the speed u and an angle alpha, which is to your horizontal, then you can split your x and y components as your x component being u cos alpha and your y being u sine alpha. So when you're solving projectile questions, once you split your motion into your horizontal and vertical components, then you just deal with the horizontal components first using CVAT, and then your vertical components, you just deal with them separately. The only thing that will be the same between your two is your time, because your time won't change whether you're going in the horizontal direction or the vertical direction. You're only going to have acceleration in the vertical direction, because that's just due to gravity. When you're like throwing something into the air, you're only going to have gravity acting on it. And remember, for gravity, your acceleration is just equal to 9.8. That means your horizontal acceleration is just going to be 0. So you can plug that in when you're looking at your CVAT. And one last thing that you need to know is that your velocity is going to be 0 at the greatest height. So if they ever asked to find your greatest height, then that would be when at this point where your velocity is equal to 0. So you can also have these your x and y components split using vectors. So you can just say, let's say your u is. So we have a question here. Feel free to pause that and attempt it yourself if you want to. So we have a particle P is projected from the ground at velocity 25 meters per second at an angle 40 degrees to the horizontal. So the first thing we want to do is find the greatest height of P. So the first thing you want to do is, when you're dealing with projectile questions, is just draw out your diagram. So if you have your horizontal here and you have your u, velocity initially is just 25, then you have your angle here, that will be 40 degrees. So that means your horizontal component, that's going to be u cos alpha, so it would be 25 cos 40. And your vertical component, that's just going to be 25 sine 40. So now we can split our horizontal and vertical components. So for a horizontal, we know that Our S is just, we don't know our S. Our U is just 25 cos 40. We don't know V. We know because it's horizontal, our acceleration is always going to be 0, and we don't know our time t. Now if we go on to our vertical components, we want to try and find this S, so we can just label S because we want to find the greatest height. U, we know that's just going to be 25 sine 40. We don't know our V. Acceleration, because it's just, this is just going to be acceleration. So acceleration, just because it's just due to gravity, is going to be equal to minus 9.8. So acceleration is always minus because gravity, remember, is acting in the downward direction. So if you're throwing up, it's just going to be negative 9.8. And then your time, you don't know your time. So now, because we want to find this vertical displacement S, which is your greatest height, we want to use one of our formulas, or one of our CVAT equations that doesn't have V in, because we don't know what. So now if we go into our vertical component, we want to find our S, so S would just be equal to S. Our U, we know that is 25 sine 40. Our velocity, because it's at the greatest height, we know our velocity, that's just equal to 0. Our acceleration, that's just equal to our gravity, so it's minus 9.8, and we don't know our time. So now we just want to use one of our CVAT equations that doesn't have t, but for something we can find s in. So we can use this v squared equals u squared plus 2as. So we just say 0 is just equal to 25 sine 40 squared plus 2 times minus 9.8 s. So then if we rearrange this, we'd get 19.6 s is just equal to 258.2. So that means that s is just equal to 13.17, which is just equal to 13 meters to the nearest meter. So what we did here is we split it up into our horizontal and vertical, and because we're just dealing with our greatest height, that's just how far it's going to be above the ground. We just only want to look at our vertical components, and then we know because we want to find the greatest height, that's when our velocity is equal to 0, and then we can just plug everything else we need to know with our acceleration being equal to gravity. So then we can just use this CVAT equation to try and find our displacement S. So now if we move on to part B, we want to find the horizontal distance travelled by P before it hits the ground. So you know that in order before it hits the ground, your particle is going to go all the way to the top to your greatest height and then all the way down. So you want to find, first you just want to find the time that it would take our particle to go all the way up and all the way down. So we can use that using our vertical components. So this, because we only have 2 values for horizontal, so there's not really much we can do until we get at least one more value that we can plug into to our equations. So if you want to work out the time takes, firstly, for it to go to our greatest height, so we can use any of our equations really. Let's go with our b equals u plus at. So if we do 0 is equal to u, which is 25 sine 40, minus 9.8t. So 9.8t is just equal to 25 sine 40. That means t is just equal to 1.639, which is just, we just say 1.6 seconds to 1 decimal place. So now that's how long it takes for a particle to go to the greatest height, and then for it to come back down, that would be double that. So your total time, that would just be equal to 2 times 1.639, which is just equal to 3.28 seconds. So now that we've found our t here, we can plug that in as 3.28. We can now, we want to find our s, we can now use our Seebeck equation, one that just doesn't involve v, but one that we can solve for s. So we can use that with our s equals ut plus half at squared. So if we do that, we have s equals ut plus half at squared. We can just plug in all our values. So s would just be equal to 25 cos 40 times 3.28 plus a half times 0 t squared. So then we just have s is equal to 25 cos 40 times 3.28, which is just equal to 63 meters to 2 SF. So that's our answer to this question. So the reason behind everything which we did is we first, because we didn't have enough information with our horizontal components to actually solve anything using our Seebeck equations, we went back to our vertical components and see if we could find another value. So we had 4 values, so we could find our time t, and that was our time t for it to get to your greatest height. So for the total time travelled by p, that would just be to the greatest height and then back down, so it would just be double of our time t. And then once we had t, we can plug that back into our horizontal components and then use our Seebeck equations again to try and find our value s. So that's just how we can solve questions with projectiles using our Seebeck equations. So now let's go on to derive some of the key formulas that you may need to do. So the first formula that we want to derive is for your time, your total time taken for your projectile, and also for your range, which is just the total distance covered by your in your horizontal direction. So as I've labelled here, from A to B, that's your range. So if we have a particle is projected from a point on a horizontal plane with an initial velocity u at an angle alpha above the horizontal and moves freely under gravity until it hits the plane at point B, given that the acceleration due to gravity is g, we want to find expressions for A, for the time of the flight. So for part A, we just want to deal with our vertical components. So the total time of the flight, that's when your total displacement is just going to be equal to 0. So it's going to go all the way up and then all the way down. So if we fill in all our Seebecks for our vertical, we'd have s, that's just 0. We could have our u, that's just going to be u sine alpha. We don't know what our v will be. Our acceleration, that's just going to be minus g, and our time, that will just be time t. So now that we've got 4 components for Seebeck, we can use one of our Seebeck equations to try and find what t is. So one that doesn't involve t, so that's our v squared equals u squared plus 2as. So we want to use one of our Seebeck equations that doesn't involve v. So that could be our s equals ut plus half at squared. So we say s equals ut plus half at squared. So our 0 is just equal to u sine alpha times t plus minus a half g times t squared. So now if we rearrange this, we would get a half g t squared is equal to u sine alpha t. So now we can cancel t from this side and we get that. So now if we rearrange to get t by itself, we'd have t is equal to 2u sine alpha over g. And that's our formula for the total time of our flight. So now if we were to move on to find our range. So as I said before, the range is the total time on our horizontal axis and the total distance covered. So for this one, we're dealing with our horizontal components. So we could just fill in our Seebeck. So we want to find our s, which is our displacement, so that would be our range. and then we want to find our u. That would just be u cos alpha. Our velocity, we don't know what that will be. Our acceleration, because it's just horizontal, that's always equal to 0. And our time t, and our t, which is equal to time, which is what we found here, which was 2u sine alpha over g. So now we can just plug in, now we can just use one of our SUVAT equations here. So we have SUAT, so we again want something that doesn't involve v. So we can use the same one, S equals ut plus half at squared. So if we plug that our values in, we would get our range is equal to u cos alpha times t plus just 0. So if we plug in our t value, that's just equal to u cos alpha times 2u sine alpha over g. And then if we simplify this, that would be equal to 2u squared cos alpha sine alpha over g. And then if you remember from our trig identity, sine 2 alpha, that's just equal to 2 cos alpha sine alpha. So we could just simplify this to u squared sine 2 alpha all over g. And that's our formula for your horizontal range. So these are two key formulas for projectiles that you may be asked to either derive, or you could just learn them and then plug it in if you're asked to find your time or your range. But I would recommend you just learn how to derive it and learn where we came from, because that's easier than just memorizing the two formulae. So now let's go on to derive the formula for our path of projectile. So to derive our path of projectile, we have a particle is projected from a point with speed u at an angle of elevation alpha and moves freely under gravity. When the particle has moved a horizontal distance x, its height above the point of projection is y. So we want to show that y equals x tan alpha minus g squared x squared over 2u squared times 1 plus tan squared alpha. So this is also called our path of projectile. So like always, the first thing we want to do is we just want to split our motions so we can have our horizontal components. I write down any information we can. So we know that our displacement, our horizontal distance, that's x. Our u is just u cos alpha. We don't know our v. We always know that for horizontal acceleration is always 0. And we don't know our t either. So you can just say that's t. And then if we do our vertical components, we know our s is just y, our u is just u sine alpha. We know that our velocity for vertical, we don't know that. We know our acceleration is just minus g, and we don't know our time t. So now we want to see if we can do like any equations. So for both of them, we see that we have a common of t that's going to be the same for both. So what we can do is we can try and find what t would be for our vertical and what t would be for our horizontal, and then try rearrange to get like maybe two equations that we can solve. So if we start with the horizontal one, what equation can we use that won't involve v? So that's just s equals ut plus half at squared. So you could say that x is just equal to u cos alpha t, just plus 0. And then if we go on our vertical, we could say that our y is equal to u sine alpha times t minus a half gt squared. So we can write down, because we know it's y in terms of something, maybe we can write down t in terms of x and u cos alpha. So we could just say that t is now equal to x over u cos alpha. And then we can just substitute this t into this equation here. So you have y is equals to u sine alpha times x all over u cos alpha minus a half g times t squared, so that's just times x squared over u cos squared alpha. Then if we simplify this, we get our u's would cancel here. Sine alpha over cos alpha, that's just tan alpha. So that's just x times alpha minus, we know that 1 over cos squared x, that's just sec squared x. So you get this is equal to minus g squared over 2u squared of sec squared alpha. And then if you remember from our trig identities, tan squared alpha plus 1 is just equal to sec squared alpha. So then we can rewrite this as being is equal to tan alpha minus gx squared over 2u squared plus times 1 plus tan squared alpha. And that's our Cartesian equation for the path of projectile. So that's how you derive it. You just want to split your projectile into your y and x components, and then just solve each one to find an equation for t, and then you can just do substitution. So you can rearrange your x to find t is equal to something, and then just plug that into your y equation, and then if you do some trig manipulation, you should get your answer for that. So that's everything, that's all the equations you need to derive for particles, and we've learned how to use this. So now let's apply this to one more exam style question. So we have an exam style question here. Feel free to pause the video and try it out for yourself first. So we have a particle P is projected from the ground with velocity k times 3i plus 4j meters per second, where k is a constant. Given the greatest height reached by P is 24 meters above the ground, we want to first find the exact value of k. So this is an example of where they've given you your horizontal and vertical components in vector form. So the first thing you want to do is you just want to split it up into your horizontal first. So you could say that your S, they haven't given that. Your U, that's just equal to 3. That's just equal to 3k. Your V, that's just equal to, we don't know what our V would be. Our A is just equal to 0, and we don't know what our T is. Now if we do our vertical, we know that our S, the greatest height is 24. Our U is just 4k. We know our velocity because if it's at the greatest height, that's just 0. Our alpha, that's just minus 9.8. And our t, we don't know what t is. So the first thing is we want to find the exact value of k. So we have 4 values here, variables here. And then if we solve that, if we plug it into one of these equations, we should be able to find our value of k. So we want to find one that doesn't involve our t. So that's v squared equals u squared plus 2as. So we could just say 0 is just equal to 4k squared plus 2 times minus 9.8 times 24. So then if you were to do 2 times minus 9.8 times 24, so that's just 470.4 is just equal to 16k squared. So that means your k squared, that's just equal to 29.4. So your k is just equal to your square root of 29.4. So that's your answer to part A. Now part B, you want to find the horizontal distance travelled. So we could either do this. So we can't use this formula because we don't know how alpha. So we just want to use our horizontal and vertical components. So because we know that t is common, we can just find, using our vertical, we can find what our t is, and then we can just double that and then use our horizontal. So if we were to find out what t is, using this equation, we could use v equals u plus at. So you just say 0 is equal to 24 minus 9.8 times, so if we use v equals u plus at, which is say 0 is equal to 4 times square root of 29.4 plus minus 9.8 t. So you just say 9.8 t is just equal to the 4 times square root of 29.4. So our t would just be equal to 2.213. So now we know that our t is 2.213. So we can use our CVAT equations again to find a value of s. So we need one that doesn't involve v, so we can use s equals ut plus half at squared. We just say our s is equal to 3 times square root of 29.4 times our 2.213, and if you plug that in your calculator, that should equal to 72 meters, and that's your answer to part B. So the key to this was just splitting into horizontal and vertical, and just recognizing that they've given it to vector form here. So your coefficient in front of your I, that's just 3, that's your horizontal velocity. Your component in front of your j, that's your vertical velocity, and then you can just solve your CVAT equations normally once you split it up in your horizontal vertical, remembering that at your greatest height of velocity is equal to 0, and that your acceleration for your horizontal is always equal to 0.